Twitch and YouTube, I figured that I'd do a short video since it's been a couple of days since the last stream. Yeah, I've been messing around with our physics system, and I disabled the old physics system, and as you can see, we have something somewhat different that is, I'd say, seems like it's functional. I'm just trying to shove this object here a bit. Uh, right now I've disabled most of the physics. As you saw in the last episode, the physics got out of whack. I decided to change the contact generation algorithm, and I'm trying to shove the model through the wall, but I can't. And yeah, I'm not using the old AABB bounding volumes anymore. As you can see, the box kind of sinks into the ground, and the physics seem to follow the actual object more closely. Um, what you can see here is like an imaginary bounding volume. This is probably the minimum corner, and this is the maximum corner. So you could imagine another line going exactly diagonal up to kind of here, and then the absolute bounding volume actually enclosing this figure. And right now we're lying on the one of the edges of the bounding volume. Uh, so as you can see, the bounding volume is allowed to actually fall down to the floor. I'm unsure. Yeah, this intersects a bit, it seems. Yeah, maybe it ended up sucking down the object. Yeah, but at least as you can see, the bounding volume is handled differently. And I imagine a bounding volume going down here. Yeah, so it's kind of standing on the corner. Yeah, the physics are not very realistic. Uh, but yeah, so this part is probably never used, so we are going to uh, not go through it. I still have the old SAT algorithm where I hard code a OBB, an OBB versus an AABB, where I hard code the AABB axis and simply do a standardized OBB versus OBB SAT test. So I collect the smallest penetration for each axis, and I store the um, best of the phase normals of this comparison. Um, and then I go onwards to the edge axis and then I do an early out if the numbers are invalid. We're not supposed to do the calculation that follows. As I've mentioned, this is basically never used in this specific collision where we test an OBB against an AABB because it's not the vertices or edges or whatever of the AABB that intersects the OBB, but exactly opposite. So we always end up in this loop or in the last part of the loop, um, where we get the collision normal from, and the which is simply uh, the separating axis, which makes sense if two faces collide. The collision normal would be alongside that face normal, since this is kind of like a face versus face or point versus face collision. The same goes for here. It means that we simply collide with the face of a polygon. And since the separating axis is calculated from within the first 6 comparisons from a face normal of either box, there are 3 face normals corresponding to each internal axis of each box. Um, we know the contact normal is equal to um, the yeah, I've misspoken. It's not the separating axis, it's the axis with the smallest penetration. We know that the contact normal is supposed to go alongside that normal, since it's uh, the plane where you get, or rather the normal of the plane where you get the smallest correcting velocity if you were to push the objects apart. So it means where the penetration is the smallest, we simply grab that axis once we have established that there's a penetration on all axes, um, and then we use that as our normal. Depending on our point of view, we may flip the normal. And then I actually ended up using a bit of GJK methods, and I'll be returning to that eventually. But I already did support functions for GJK, um, and I wanted to use the contact normal and the contact face for finding the so-called contact points. Contact points are where uh, we have an intersection, and since we're handling box versus box, it's possible for a box to collide with another box with a plane. For instance, or rather not a plane, a face. So a face versus a face collision, depending on the size of the boxes, allow for up to 4 contact points. 4 corners of the box can actually collide with the surface on another box, and all 4 points would be contact points. If the collision happens head on, we might end up in a situation where only 2 contact points actually collide with the surface, or maybe even only 1. Or in I guess depending on how deep the penetration could end up being, you would end up with 3 contact points. Anyway, I decided that once I have the face calculated, that um, that we collide with, I want to, from the normal itself, calculate what is the actual midpoint of that plane in world space. And for that, I use um, a box function, or rather support function for an AAVB. And since this is not rotated, I can be fairly certain that the X, Y, and Z axis internally for the AABB always is the same, are the same. Therefore, I simply use my half widths and my center point to derive a set of opposite midpoints for each face of the box, and then I calculate the dot product between the contact normal and the actual midpoints of this. Yeah, it's not box, line series or point series, and I find the point where the point points as much as possible in the same direction as the contact normal, meaning that we find the midpoint of the AABB in whatever direction our contact normal is. That means that we actually get a point on a plane, and since we have a normalized, or rather a unit size normal, this is normalized, so it will have a magnitude of 1. Since we have a normal with a magnitude of 1, and since we have a point on a plane or a face, plane face, it's kind of the same here, we can actually use a bit of plane intersection testing to do calculations on what points are either in front, or rather over, or yeah, in front slash over the plane that we create from the point and the contact normal, and what points are below it. And we can actually use that for our intersecting object, meaning that if we have a totally aligned collision between two faces, the lower box will be standing still, and the box on top of it will be sinking a bit down through the lower box, and potentially all 4 corners will intersect. And since we have the midpoint along the contact normal on the lower box, we can simply define that upper face or surface as our plane, and use an algorithm that's also a kind of support function, where we ask, well, which vertices in the other box are below that point, or yeah, we do the dot product of the point on the plane and the plane's normal, and then we have a d once we do a dot product between the normal and a an arbitrary point. We know that if d is the result of that is the same as d, the point is on the plane. If it's lower than d, we are behind the plane, and if it's higher than d, we are in front of the plane. So we simply, this is because the bounding volume is oriented in space, and we have to calculate the 8 vertices for it. if I end up using this algorithm. Eventually, I'll of course have to do this probably more efficiently, but for now we do it like this. And right now it's not a problem, but once we get more boxes, we might want to calculate the corner vertices and everything at a pre-calculation step, and simply just use some memory to pass it along. But anyway, we calculate the 8 corners of the box in with world space coordinates, and we simply do a dot product between each point and the plane normal from the point, or rather the plane we created earlier, and we simply ask what vertices are under this plane. And we or rather behind this plane, and we simply end up with a list of vertices that are the current contact points that have intersected between objects OBB and object AABB. So this is the robust part of the algorithm. I think it works, yeah, I dare say almost perfectly. The problem is that we have edge cases where I kind of do the same. Right now we do not have edge-edge collisions. It's very, very rare. In reality, I suspect that you could use a resolution of the collision which is based on a edge versus face collision where the OBB edge collides or penetrates a surface on the AABB, because in reality the current setup or the way the objects are created, we're not actually having a lot of edge collisions. So yeah, this is a part of the algorithm where I might end up improving upon it, and I'll still come back to how to use the SAT eventually. But yeah, I basically the only difference between this part of the algorithm and this part of the algorithm is that here I do not have a small enough separation along a specific face of either box. So therefore I use the cross product of the smallest, or rather the two different axes with the smallest combined interpenetration of the OBB and AABB. And then I, of course, normalize it and make sure that it is pointing away from the AABB, which is always the object that we collide with in this situation. And then, as before, I calculate a midpoint on the face on the specific AABB, and I simply cut off every point behind that plane created from the midpoint and the contact normal in the OBB, and I get the contact points. So yeah, this should eventually be edge specific calculations, and that is what I wanted to talk about today. I know of a SAT algorithm where instead of overlapping axes, um, we use a mix between the overlapping axis and the GJK, which or rather, not we, which I implemented off stream the other day, um, and use the support functions to find the specific points of whatever box interpenetrates. I think it's the most, and you are able to handle face versus face collisions and edge versus edge collisions a bit more, um, how do you say, robustly. So you can always be kind of certain that you have a face versus face collision, and in an edge versus edge collision, you would just simply calculate the closest points on each of the edges and set that as a singular contact point. Um, yeah, but right now the algorithm doesn't support it. It's not really needed right now, but yeah, for everything to be entirely robust, I would simply prefer um, to implement that. But yeah, as you can see, oh, I have a bit of screen tearing here, I can see. Uh, but as you can see, even though I push it up against the wall here, I really try. As you can see, it doesn't go in. The object is kind of like allowed to fall on. Yeah, you can see it had a fairly long way down until it actually collided with anything there. And now it's like it's standing on an edge. So it's not, as I've mentioned, not using the bounding volume that is drawn around it anymore. It's using the OBB, which is pretty great, and it doesn't fall through the floor. And yeah, so in the physics algorithm, I haven't really implemented the final algorithm. I'm still playing around with that and finding out how to build a system that is fairly robust and not and that doesn't look like uh, um, something that is out of this world. Um, yeah, but basically for each, let me close this one. We collect collisions, contact normals, contact points, penetration depths, and we have some um, context space transforms. Yeah. Which is another thing where you can transform from world space to so-called context space, where the contact normal is a certain axis and so forth. I showed you a bit about it in the previous episode where we had the totally whack overly rotational physics implemented here. Um, but yeah, for each collision, we have a set of contact points. Usually it's more than um, one, but it can be one. And we calculate where we are in world space relative to the center of the body, where we calculate the angular inertia tensor uh, relative to the world for this object. Then we um, calculate some angular inertia and the linear inertia, and then we update the positions. We take into account the penetration depths, of course, the contact normal, and uh, The linear inertia. Ah. What about the angular inertia? I'm pretty sure it's supposed to get added. Let's try to add it in. And let's see. I'm not sure whether this is entirely correct. Let me just disable screen sharing. I think that will be. Yeah, definitely looks way better. Anyway. And as you can see in the background, we get a dump of the contact point between the floor right now and the object, and we're 18 along the x-axis. We're a bit below the 0 point on the y-axis, and we're pretty close to the z-axis, meaning that we're probably around here. And if we imagine that a uh, um, separate diagonal of this invisible OBB box actually goes down and ends up somewhere around here, we can actually imagine that it's probably standing on kind of like one corner or something. Yeah, anyway, but collision checking works. Let's see if I don't disable the velocity, do I get some weird results? We get a lot of jittering, and yeah, the forces are getting calculated somewhat oddly. So the object just yeets out of existence. Yeah, we definitely need to solve how to actually apply forces and position corrections uh, whenever we have a collision, but that is for a future video. Yeah, so if anyone are if someone is in possession of a SAT-based algorithm where you use support functions more thoroughly during the actual collision checking, where you can get more specific edge and face information, feel free to hit me up. Otherwise, I'll look into how to implement the method myself. As you can see, I already implemented some support functions, so I'm guessing that implementing such an algorithm is not extremely difficult once you get the overall principle of this um, algorithm, and this is actually the second or third version I'm trying around with. Yeah, but all of this is actually developed from scratch. I also know that for boxes that are smaller, you would want to do clipping alongside not only the plane that is perpendicular to the, or rather not only the face that is perpendicular to the contact normal, but you would also want to clip off and create new points for every point that on the parallel faces, which goes along the same direction, or rather that would yeah, the other faces that are not perpendicular to the contact normal, or the separating axis itself. You would also like the points to be cut off by the other faces, extended, of course, through space, since you can't have contact points that extend past the surface of the actual contact. If that makes any sense, let me draw it out for you. Let's see, I don't care. So if we have a surface here, if we have a small box that lands on it, it's fine. These potentially four corners are all fine. What an awful box. Anyway, these four corners are all fine, but what if we have a massive box, like something like this? Let me draw it out right. This box here is standing on a smaller box. Yeah, I'm not gonna redraw that surface, but let's see. A smaller box here. I mean, there would be no sense in creating a contact point out here, even though it's part of the surface that might penetrate down through this surface of the smaller box. So you would rather say, well, I have a contact point offset, a contact point here, a contact point here, a contact point here, and a contact point here. So you kind of like use a cutting tool where you cut off kind of all this past surface area of the bigger box, and you kind of recreate an offset vertex in here, and offset vertex in here, offset vertex in here, and then define these as your contact points or support points, or whatever you, and this as a so-called supportive feature. So yeah, that is missing from this algorithm because it's not a generalized algorithm yet. It's work in progress. I had to figure out how to do a lot of this different stuff myself, and I'm not an expert in math or in these algorithms at all. So yeah, I had to spend a lot of time of playing around, and it only got working in the degree that it actually works right now. Since this evening. So for instance, if I simply dump out this every time and dump out this every time, you would be able to see in the console whenever our algorithm generates a contact point. You can see for each collision how many contact points are created for that specific contact, or rather collision. So yeah, as you can see right now, the axes of each volume are perfectly aligned to our world space coordinate system. Therefore, the plane, or rather face, with the smallest separation is going to be the plane that is perpendicular to the y-axis on the positive uh, side. But anyway, the plane, no matter how uh, we offset it, it's that plane that separates the objects, or rather not separates, that they have the smallest interpenetration on, because the axes of the objects are perfectly aligned. Therefore, whenever the OBB sinks down into the AABB, which is the floor, the vertices, or corners of the OBB align perfectly, and therefore all four gets cut off by the algorithm. And as you can see, they only have to be just a tiny fraction below the AABB surface before they get clipped into a contact point. Once we kind of offset the object, you can see we end up in a situation where we usually only get one contact point, or one primary vertex. Sometimes we might end up in a situation where we have two. Whoops. Yeah, now I crashed the algorithm, but I'm not sure whether I can find anywhere where it actually uh, tells us that we have two. It's probably mostly singular points. Anyway, you could, of course, do um, contact caching, meaning that you could do different ways of resolving the contacts. Maybe you want to collect maybe you want to allow the algorithm to have several contact points. As you can see, we got an edge version very seldomly. Actually, during the whole process, we had around, okay. As you can see here, we had two contact points in this collision. Yeah, the edge collisions are actually handled a bit more like real edge collisions. So yeah, whenever an actual edge seems to collide, we actually do get two contact points. So maybe this part of the algorithm isn't too bad after all. Yeah, we could always evaluate on that. Anyway, yeah, so this algorithm works fine, but I think, excuse me, that a better and more robust implementation could be implemented, and I find it kind of fun to tinker a bit around with. And then, yeah, maybe next weekend I will do a bit more work on the actual physics. I mean, at least now we have an offset for handling contact generation and basic collision handling. It seems like our system is robust enough to find points of contact in world space, kind of like no matter what surface we collide with. I haven't shown you, but it obviously works with the other planes or rather the other object as well. So yeah, that is great. It feels good to actually be able to derive something like this. It took a lot of work, and definitely it's not as robust as you'd like or as complete as you'd like. But yeah, it at least gave me a better understanding on what we're actually doing inside the physics engine itself, and hopefully it will be advantageous to have that information as I go along forward. Needless to say, I really look forward to having a complete physics system. I of course have to read a lot of different resources to know how to do this, but I think that being able to do things a bit your own way is fun. And yeah, I'll rework all these algorithms eventually as well. I started with the hardest project in terms of collision checking, which is basically OBB versus OBBs or polygons of uh, um, different counts of edges and faces. SAT kind of supports uh, different polygons, and GJK also does that. So yeah, that's definitely way harder than handling a sphere versus a box. But yeah, we implemented a sphere collider for the player controller, if you might remember, which is basic stuff. And then we do some localized collision checking. Um, yeah, so yeah, spheres are way easier than polygons or just even OBBs, especially when they have a rotational aspect to them. Um, so yeah, I definitely started with the hardest problem, and once this gets resolved into an robust algorithm that I like, and we are almost there, um, then the other parts of the collision checking is going to be fairly easy. But yeah, then the algorithms will get reworked. I'll make sure that I don't calculate the boxes too often, and I might even cache them inside the bounding volume or as a separate data structure. Yeah, yeah, I might do that. Uh, and then we have to, of course, rearrange this code into a complete physics interface, which will hold our data. Then after that, I'll refactor the different data structures inside this area, and do a bit of work on how the data is laid out and stored, created. And then I'll probably look into the different algorithms and whether they could end up being a bit more data driven, or rather in a bit more data oriented design. This has been from the get-go a plan of using not as much object-oriented programming, but instead going for a more procedural slash data-oriented design, where you only use objects and object-oriented coding for like creating some basic helper structures with a bit of added functionality, but where you don't bind specific data to it. Since the principle of data-oriented design is to kind of separate your data from your methods in sort, like so that you can do operations to arrange your data, then process your data, then output some data, then rearrange that potentially before you process it even more, output it again, rearrange, process, output, until you have done whatever you need to, so that every data is kind of like organized and then fed into a pipeline where the CPU can use as much focus and potentially parallelization to handle the computations. And then output the data. And of course, the data has to be arranged in such a way that caching and everything is fairly efficient. Right now it's totally beyond the scope of this project, but I plan to do a hobby project alongside this that I think would be fairly nice if it was able to handle large streams of data. So yeah, that is it. I just wanted to give an update and show a bit about what I've been doing lately. I think for a total non-professional programmer and such a game development noob as myself, I think the process has been painful, but definitely interesting and enjoyable somewhat in the end. In the end, it definitely has been enjoyable, but it has also been quite painful. Yeah, a couple of days ago I had no real sense of how to use planes properly, how to define planes and do calculations with them, and now I feel pretty comfortable doing most of them. So yeah, Minkowski differences and everything is something I'd never think I'd get into, but here we are, and it's pretty great. All I have to say here in the end is remember to appreciate your dot products, your cross products, and remember never to do as I do, and that is never to develop your own math library. It's painful, but also a bit fun if you like SimD. Anyway, keep it cool. Thanks for dropping by. Feel free to comment, like, or subscribe. Or if you have information on the SAT algorithm that is implemented by using support functions where you find the most interpenetrating vertex of each box, let me know, because I would like to play around with that algorithm. Alright, I'll be seeing you around. Bye bye.